Welcome again, Vitas, to a new lesson. So today we'll finish the product rules, and you can see the green dots. They are the properties that we have already proven, and today we'll see number 4, 6, and 8. And I've written here as a reminder what are the translations of the gradient, divergence, and curl into index notation. So we are given this. I'm going to start with number 6 because it seems to be like shorter. Okay, so let's prove that this is true. So we are going to translate this into index notation, and let's see first of all like the cross product between A and B. This is given by epsilon ijk, and we contract A with the second slot and B with the third slot, and our free index, because remind that this is a vector, so the free index is this, the I. However, the free index of this vector is contracted with the other index of this other vector, because we told that nabla could be thought not as an operator but also as a vector. So we have to contract the index of the del with this vector, and we have to remind ourselves that this is acting upon all this thing. Okay. So the Levi-Civita symbol is constant, so we can pull it out from the derivative, and we are left with this. And now we are going to apply Leibniz rule. Remember from the last lesson, the properties 3, 5, and 7, they were all Leibniz rule. So this is just this thing. And now we are going to see, we are going to distribute the epsilon ijk and now probably you are going to see where I'm going. We are going to arrange the indices of the epsilon, well, of the Levi-Civita tensor. So first of all, remember that if we change any pair of indices, we have a minus that it swaps with the indices. So for example, it will be ikj. If we swap indices again, another minus sign appears, so this will be epsilon kij. So we can change the first one by this very same thing, epsilon kij with del I aj. And now for this other one, we can write epsilon ijk as minus epsilon j ik. Okay, so now you can see that we have this structure, okay, with this one and also with this one, and they are curls expressed in index notation. So how do I know how to swap the indices? Well, you can guess by simply seeing that this is going to be the second slot and this is going to be the third slot of the Levi-Civita symbol. So I want the I index to be in the second slot and the J index to be in the third one. So necessarily the K must go to the first slot. And the same with this other one. I have I and K, so I want to place the I and K in the second and third index, and the J is going to move here in the first slot. So this is just like the kth component of the curl of A. This is like the jth component of that vector. No, I'm sorry, it's like the kth component of that vector, and now we have bk, and here we have the jth component of this vector contracted with the vector A. So if we translate back to the vector notation, this is just going to be the vector, which is the color of A, in dot product with B, minus the color of B in dot product with A. And this is the very same thing that appears here as a property. So moving on, we are going to see now number 4, for example. And we are going to expand this thing. So this, in index notation, is simply, well, you have first to observe what we have here, because in the previous one, we had just a scalar, okay? Because we had a vector contracted with another vector, so this was a scalar. There were no free indices. However, here in number 4, we have a scalar and then a vector. So this is going to have this is a vector. So we are going to have a free index. And the free index here is going to be the one from the nabla, which is just the index I in the del. So this is just, for example, AJ, BJ. You can put here the letter you want, K, you know, it's a dummy index. And we're going to do Leibniz rule. So this is del I, AJ, BJ plus AJ del I, BJ. So now we are going to do a trick, okay, which is we are going to copy the exact same thing. I'm going to drop the parentheses because it's going to be like understood that what's in the right hand side of the del operator is what's it's deriving it. And now we have, okay, so the trick here, I'm going to add, and also I'm going to take out the very same quantity. So for example, I'm going to add bj del j ia, and then I'm going to subtract bj del j ai. It's the same thing, okay? So this is like plus 0. Why do I do this? So we are looking at the first term, and the idea is that we are going to maintain bj exactly equal. You see here that it's equal. However, we are going to change these indices. So you see here that it's first I and then j, and now it's j and then I. Okay. Now we are going to do the same thing for the second term. We are going to do plus aj, and now we swap del j bi, and now we have to subtract the same thing so that we don't mess up the equality. Okay, so we are now going to pull some factors out. Okay, we have bj del I aj minus del j ai plus bj del j ai. So all these terms, this is this first term, this is this other term, and this is this other term. Okay, so these are the 3 terms related with the b in front of the term. Now we are going to do the other one, which is basically aj, and now del I bj minus del j bi. Okay, now that we have this in a much nicer way, first of all, note that this second line is just the first one, but we have swapped the a by the b. So we are going to make this abbreviation, okay, we're going to erase this line, and we are going to write simply plus the same thing, but we interchange a with b. So we're going to recall ourselves of the Kronecker delta very fast. So if we have ai delta ij, we kill the repeat index and we place in the other one. So this will be aj. So the Kronecker delta collapses indices. Now we are going to see that this also works. For example, if we have, I don't know, km and we have del m bj, we can kill the m and put in the k. So we're going to do now a little trick, which is that we are going to interchange the I index with m, for example, and the j index with n. So we are going to do that by saying that we're going to interchange I by m and j by n, and we're going to write del m am. So if you carry out this product with the Kronecker deltas, you can see that it's exactly the same thing. Okay, so this delta, it kills the m and places in the I, and this other delta, it kills the n index and places in the j. Okay, so this is the very exact same thing as this one. Now we are going to do the same thing, but we are going to maintain the del m an. So now the deltas are not going to be the same as the first term. So for the del j, we are going to interchange the j this time by the m. So we are going to have del jm. And now we are going to interchange the I index with the n. So we are going to have delta in, and now the same thing, del m and an. This is going to say the same thing, and now the same thing, but we interchange a with b. So now we can pull out this factor, which is del an, and we have bj del m an. The del operator only acts upon a, and now we have this thing. So you can check by yourself that, well, I think we have a video, it's a previous lesson, where we demonstrate a very important identity. And we are going to transform this into the product of two Levi-Civita symbols. We finish to copy the rest of the line. And now we can see that this is basically epsilon ij. Now we need a dummy index, for example k, with epsilon mn and the dummy index k. So if you want to see where this comes from, I have a video. It's a long video, and it's only proving that this is true. We use this identity also here, I think in the second one, or maybe in the first one. Well, we used this identity previously, so we are already familiarized with this thing. And now we have to finish to copy this line. So now the interesting thing is that we can write epsilon m and k is the exact same thing as epsilon kmn, because we have swapped two indices. So minus minus is plus, so it's the same thing. Now we are going to have epsilon kmn del m an. I think you now see where I'm going. And then we have epsilon ijk bj plus this other stuff I'm not going to copy over and over again. So this, you can identify this with the curl of A. So this is just the kth component of the curl of A. And now we have epsilon ijk bj. So let me reorganize this really fast. Okay, we can move these things like this, plus the other stuff. And now we have again another, we have now a cross product. So the cross product is, we can see here, the free index is I. Note that we started with the free index I. The free index is going to stay always as the free index. There may appear dummy indices, but the free indices always stay the same. So we have the free index in the first slot, which is good. Then in the second slot we have the b. In the third slot we have the kth component of this vector. So this is just going to be b cross curl of A, and this is a vector and it's the ith component. And now we have this term. You see that there is like a dot product between B and the nabla vector, so we can write this as B dot product nabla, and now the vector A. It's very important, okay, this is not equal to A B dot nabla, and it's because this doesn't make any sense. The nabla needs to operate on something, so the nabla is operating in A, so we can't swap now things, so this has to stay like compact, you can't move around things. So this is the ith component, and now we have to interchange A by B, and now we can translate this back to vector notation. So this is just simply B cross curl of A plus the dot product of B with nabla acting on A, and now it's the same thing, but we interchange the B by the A cross curl of B plus A dot product with nabla acting upon B. So we can check that this is the same thing. We have A cross nabla cross B, it's here A cross nabla cross B. Now we have B cross nabla cross A, B cross nabla cross A dot nabla B, A dot nabla B, and B dot nabla I. Let's go for the last one. We have done 4 and 6, and now we are going to do number 8. So in number 8 we have the curl of the cross product between A and B. So this in index notation is basically, we are going to stay with the I as the free index, and this is epsilon ijk. Now in the second slot we have the nabla, which is going to be del j, and now here we have a vector, and that vector is the cross product of A with B. So we have to write here the kth component of that vector. So A cross B is simply ijk aj bk, but we have to change the indices so that they can fit in here. So here we have to put the vector, but the free index is going to be k, so we are going to have epsilon k, and the other dummy indices jj, kk, we are going to change their names, so they can be, for example, mn, am, bn. So this is the kth component of this vector. Okay, we remember that the Levi-Civita symbol is constant, so we can pull it out of the derivative, and we have epsilon ijk, epsilon kmn, and now we are going to do Leibniz rule, which is basically bn del j am plus am del j bn. So we are going to do the same thing as before. The product of two Levi-Civita symbols is a linear combination of the product of Kronecker deltas. So this is just going Crocker delta mi nj minus mj ni, and this is times this exact thing. So we are going to distribute. I'm going to do this really faster than usual. And now it's minus okay. So now we are going to contract all the Crocker deltas. So we have in the first one nj and here an n, so we are going to place the j in the b and mi with the am, so we are going to replace the m by the I, and we are going to do this in every term. So we are going to end up with bj del j ai plus ai del j bj minus bi del j aj minus aj del j bi. Now we can translate this back into vector notation, and we have the dot product of b with the nabla acting upon the vector a plus a times divergence of b minus b times divergence of a minus the dot product of a with nabla acting upon b. We are going to check if this is true. We have b dot nabla a minus a dot nabla b minus a dot nabla b, a divergence of b, a divergence of b, minus b divergence of a minus b divergence of a. So we have finished proving product rules. So in the next video we are going to prove the second derivatives. So see you there.